Welcome to another podcast. In this episode, we're going to be taking a look at a specific example of how to do the inverse transform of a function involving the convolution. Now, in the past, we would have done this particular problem by looking at something like the following. We would have said, okay, what is the inverse transform of? And then we would have said, okay, well, I've got factors down here, so I'm going to do partial fractions. And so up until this topic was introduced, the only way we had of really doing this problem would have been to express it like this. And while that's okay to use partial fractions, we've experienced that on some of these it can be very frustrating if there's multiple quadratic factors or if you have a factor that's repeated. This can be a very frustrating process because you can end up with several variables. So instead, I want to take the inverse transform using convolutions. So what would this process look like with the convolution? Well, the essential way in which it's different is I want to think about the left-hand side of this as being some f of s times some g of s, and then the answer will just be f of t convolved with g of t. So the question is, what is my f of s and what is my g of s up here? Well, I need to pick f of s and a g of s. I need to pick the factors here so that I easily recognize their inverse transforms, little f and g. So the first one that comes to mind here is s squared plus 4. That's a sine or a cosine potentially, but the 2 here just locks it in. I should look at this one as being 2 over s squared plus 4, in which case f of s would be 1 over s minus 1. Now my reason for doing that is both of these are transforms that I should easily recognize. So the inverse transform of 1 over s minus 1 times 2 over s squared plus 4 I can express as being the inverse transform of each piece, convolved instead of multiplied. So in other words, this distributes, but it distributes, so this distributes across convolution, not across multiplication. And so this would be 2 over s squared plus 4. And so 1 over s minus 1, its inverse transform, you should recognize that as being e to the t. And 2 over s squared plus 4, you should recognize as being sine of 2t. And so the convolution there is simply just e to the t convolved with sine of 2t, which we know integral-wise, so our answer here, integral, using the integral form of the convolution, would be the integral from 0 to t of e to the u sine of 2t minus u du, or if I didn't like the way that integral looked, I could also write it as e to the t minus u sine of 2u. This one looks a little bit better. And this would only require one pass of integration by parts. Rather than do that out completely on this video, I just went ahead and dropped the integral here into Maple. And so the return here is this, which we've seen things like this semester, so that's not a surprise. But the return here is the inverse Laplace transform is given by this result. And so we trade the complexity by hand of partial fractions for the potential complexity of finding a definite integral. So definite integration can bring its own set of challenges, but this can be easily done in calculator or computer or something like that. And so there's a lot of benefit here to understanding the convolution, but it's not going to save you a ton of energy over partial fractions. It's just a different way of thinking about what's going on in these particular problems. All right, thank you for watching.